parte quella in inglese. So now we try to conclude the third part of this lecture, which was focused on the system identification of parametric models. And in particular, we will try to, which is called instrumental variable method. The acronym is IVM. And so what is the main idea? So the main idea is to exploit the least square method, but we know that if we use the least square method with models that are not in the form of Rx structure prototypes, we will have inherently estimations that are biased and not consistent. So let's try to use the same algorithm, the same solution, but in order to obtain also solutions that are consistent and uncorrelated, so consistent and unbiased, also when the disturbances are uncorrelated. So let's start with the basic, again, with the least square method. So if you, again, consider a least square method, you remember that the output is given in this compact form, is a vector form, where the vector phi is contains, again, in the assumption of single input, single output model. So we have one output and one input. Even if in MATLAB, we will see that you can apply this approach to multiple input, single output, and also in the most general case, multiple input, multiple output. Even if, as we have already done in other courses, we are decomposing a system with multiple output as a collection of systems with multiple input and a parallel of a number of systems with one single output. So we are considering a system with m outputs as a collection, as a parallel of m systems with each multiple input and each one single output. So it's easier than a single block with multiple input, multiple. So for this, our investigation, we are assuming single input, single output, and we have the least square approach. So we already obtained that the least square estimate has this form. So the main problem is that to guarantee, if you remember that this is non-singular, because you need to invert it, and so this is not zero, and this is something is finite. And when you are performing the estimation error, of course, we are neglecting here the term. Sorry, I forgot to start the open board. Okay. Just because I noticed that there's here we have the expected value of this variable, but because you can assume that this is theta 0 is a deterministic value, and because also the estimation is deterministic, so you can neglect here the symbol of the expected value, and when the number of data tends to infinity, you can drop this symbol. So it's why also to simplify the notation. So if you assume that this term is always different from 0, you can invert it and is always different from 0. So in order to have that your estimation is consistent or not biased, you need to have that this term is equal to 0, if you agree with it. So in order to have this, we need that the expected value of this product need to be 0. So it means that epsilon needs to be uncorrelated with respect to phi. And we said that this formula, this expression is true only if the epsilon is a white noise. So it's the case of the Rx. And so in general, when you have that epsilon is not a white noise, it means that the least square estimate is not consistent. So let's see how we can maintain this condition even if for models that are different from ARX prototypes. So the least square method is just to highlight some advantages and drawbacks. The least square method is simple and computationally also easy, but the problem of the least square method is not consistent for estimates with the correlated noise. You could use, as we saw the last time, the prediction error method. The prediction error method is valid for more general structure, and it has good properties of the estimates. The only problem, which is highlighted here, is computationally high demanded. So it's very complicated because it requires a numerical approximation, a numerical solution. So we propose a third approach, which is called the instrumental variable method. The instrumental variable method, which is the problem of the instrumental variable method. Of course, the problem is that it can be applied also for more complicated structures when the noise is correlated. And of course, because it's the instrumental variable method, so it's like a variant of the least square, so it doesn't provide a modeling of an accurate modeling of the noise. So it's limited to a very simple solution. But what is the advantage of a least square? So it maintains the structure of a least square, is simple and computationally efficient, is consistent also for correlated noise, unfortunately is less robust and statistically less efficient. So you obtain, so it's something that is in the middle between the PN and the least square. It's something that is simpler, but the accuracy of your solutions is a little bit worse than the prediction error method. So it's something in the middle, but it's like a trade-off. So what is the basic of your instrumental variable? So you need to, it's quite simple because it says that you are introducing what we call the instrument. The instrument is a variable z of t, which is important, is a signal which is uncorrelated with the prediction error. Of course, when you have a sufficient number of data, and of course this is the solution. So if you have that this instrument is uncorrelated with epsilon, you have that this expression is 0, so it means that you have a consistent estimate and also is unbiased. And of course, if the inverse exists, you can obtain this solution, which we can call it the solution of the IVM. As you can see here, so the idea I'm highlighting, you are replacing, instead of phi here, you are replacing an instrument that has uncorrelated with y, but of course in the expression you need to replace this instrument also, so it's like a replacement of a variable. Of course the solution is very simple, but how we can obtain this z signal, because the idea is very simple, it's trivial. How we can generate this signal z? Again, so instead of phi, we are using this instrument z, which is uncorrelated. The idea is that it is uncorrelated with epsilon, but should be correlated with phi. Because if you see here, if this instrument is uncorrelated with phi, means that this matrix is cannot be inverted because it's singular. So the elements of Z are usually called instruments. Of course, note that if Z is equal to phi, the IV estimate is trivial, is the same of the least square. Of course, you cannot do it because the Z is correlated with epsilon. So this is the way to the choice, how we choose the instruments. Of course, this is something that is automatically done in MATLAB, Simulink, so you don't need to do it. So a possible way for selecting your instruments is very important. So this is the recipe when you are preparing a cake. This is the recipe. So Z needs to be uncorrelated with epsilon, such that you have this, and Z should be correlated with phi, because these matrices need to be inverted. In other words, though this is the point, it's essential that Z and phi are correlated. So how you can generate as an instrument which is correlated with phi is quite simple. In practice, you can choose these instruments by filtering the inputs of your system, because you know that the output phi contains the output, and the output is correlated with the input. So in order to obtain a Z which is correlated with phi, it is enough as a first solution to take the inputs, the same input, and like an output, and then eta is obtained by filtering the inputs. Is something like you are using another ARX model to generate your instrument. In fact, this is the idea. the simplest, even a simpler, well, the simplest way for generating the instruments is to use the same inputs. Because if you remember that Z needs to be correlated with phi, but phi contains Y, which is correlated with U, so put in the vector Z the same inputs. So this is a very simple idea. So in fact, this is the way for implementing so you have two possible ways for implementing the instruments. One is the filtering of the inputs. The second is to use a suitable number of delays of your inputs. Again, because the point is here. I'm coming. It's essential that the instrument Z is correlated with phi. So this is the trick. So to me, is fine, that is enough that you just understand what is an instrumental variable. I don't want you to enter into the details of, because the specific how to generate the instruments, just to have a very light idea of this method. And of course, because this is working, because you have the other assumption, as we said, that U is uncorrelated with epsilon. Not only uncorrelated, but is something more, is independent. Because of course, you know that U is deterministic and epsilon is stochastic. So is stronger the condition of independence than the uncorrelation. So was just a sketch on this method. So so the implementation of again just an overall summary of our schemes. So the PM is the strongest in the sense that it provides the most accurate solutions, but of course the PM is also the most complicated. LS is computationally convenient, of course, if you can use it. So it means that you can use the least square approach when you limit your estimation to FIR or RX models. The instrumental variable method uses instruments. So it's something that we can call it as a LS-like. So when you say LS-like, means is similar to the least square solution. So this selection of the instruments make the solution consistent. This is the point. Let's say the drawback of this approach is that the instrumental variable methods provides that the estimates are consistent. So it means, again, consistent, that the estimation is near to the true, so let's say true solution, but the variance, so the estimation error, is higher. So the accuracy of your estimation you obtain with instrumental variable is a little bit worse than the PM estimate. But of course, the instrumental variable is simpler in its implementation. So it's something that is like a trade-off between accuracy and solution complexity. So this is it was the last part of the estimation of